more slides, but we actually, so last brunch, this was several months ago because there was a break before the Christmas hiatus.
I believe it was 10/10/25 in
Yeah.
September,
So we gave a talk on Scylla and
October.
Amprius, and I think Ronnie here in the call was kind enough to reach out and be like, "Hey guys, do you mind re-rating? And if I show you more solid concrete evidence?" And that manifested itself in another talk, and we got to see a lot more spec sheets, and we got to see a lot more design, and got to get a lot more insider info in terms of what is Amprius doing, what are they doing really well, and because of that, we actually, from whether we like them, we bumped them up significantly,
We,
mainly
we, we
because
also we also I believe increased their engineering into the box and their pain points.
exactly.
Those parts we're not showing here, but they're updated in our original slide deck, which is available on the Battery Brunch notes website.
Exactly, and we updated the total aggregate score as well. And the reason being is they shared some stuff. So I'll give you an example for engineering into the box. We think of Amprius as the company that does silicon wires, and they still do, that direct growth deposition. But they are also a company with a standard silicon particle approach. So they have basically multiple product paths, which is fantastic, and which is what you need to do if you're trying to do something really advanced, but also if you're trying to do something new, right? So you need to have a lower bar and a higher bar. And he explained that, we showed a slide on, I think it was, Ronnie, correct me, but it's Amprius, which there's a slight name variation, but they are actually doing particles in their standard slurry coating. So we said engineering into the box went up because they're actually approaching it similar to Scylla in one of their avenues with producing particles, right? And as far as pain points go, we upgraded too because it was shared with us that, yeah, they have pilot lines. They're able to produce a lot of cells. Their biggest issue is just getting more equipment because we're in the middle of a pandemic where supply lines are hard to get.
Stretched to
And
breaking.
yeah, and it's unfair to negatively rate a company if you got to deal with something where you have zero control over being able to get the equipment. So they are producing, and they're actually, their biggest thing is they're trying to meet customer demand, right? And that's one of the things. So this is what we wanted to share. The reason being is because we want to show that we're not only open to changing our scores based on like data that is provided, but also we want to be truthful in that sometimes the things we say aren't 100% accurate because we're doing research like the rest of you would using the internet and trying to find what is publicly available, right? So this is just us trying to be as transparent as possible and show you guys as many of the things, and then share with you that Amprius was willing to come forward and share with us a lot of data. And they actually shared, and this is kind of a slide from them on the left. This is how they view themselves, and they view everyone else. One thing we did cache here is Oxys is no longer should probably not be high on the commercialization scale as they
Since they died.
so a little bit of a catch there,
It
Ronnie.
usually takes a year and a half for marketing slides to update. So we'll give you to let's say June. How about that?
Yeah, you're right. Yeah, thanks, guys.
So we figured Oxys shouldn't be that high, but it's really cool. So we're actually going to start providing people who provide us their slides, right? We're willing to show. So we have Amprius here on the left where they see themselves versus where they see all their competitors and everyone else. And on the right, we have what Enovix was providing in terms of how they are relative to the rest of the field.
But they seem to not be covering startups. They're only covering big commercial entities. So we were really hoping to see, maybe like, the on one end you have, them, Amprius to them, and I was going to guess they were going to show the reverse of them in front and Amprius in the back, but they didn't choose to share any startups.
Yeah, and one of the things here too, guys, right, is remember that, like, if you look at it, it's pretty interesting, right? So Amprius is putting themselves at a very aggressive target, which I'm a big fan of Ronnie, so I hope they hit this, and I hope a new battery, actually in general, I just hope a new battery technology hits the market because it would help validate every other battery material startup and give more traction. But it's interesting to see Enovix here at like 300, and you can see Ronnie has them, or not Ronnie, but Amprius has them near 400, I would assume, if that's 5.3, and this is the dead center.
Yeah. So the information that I provided you, we have a commercialized 450 watt hour per kilogram, and we have 500 in the lab. And we don't like to promote things that we have in the lab. It's part of that whole, people promoting things that aren't real. Everything we say is stuff that we have things to back it up with data sheets. So yeah.
But yeah, so like this is just us wanting to provide more data, be more transparent, and share with everyone what things are available out there and what people are telling us from the companies we're talking about, right? We're just trying to be as informative as possible.
And as a specific thing, I don't think there's anyone from Enevate in the audience today, but if there was, we would love to talk to you guys, because basically it was an I don't know on just about every single thing in the grading criteria, because there's just not enough public information to really make a call. So we'd love to talk to you, and if you talk to us, maybe your score goes up. One other thing I thought was interesting is I'm sure almost everyone here has looked at the battery report that just came out. And we had picked these 4 companies to talk about, I think, as far back as April or May of last year. And I just think, and so in many cases, they had not gotten their big recent investments at that point. So when we picked them, it was more of the ones we thought were interesting and different enough to talk about, to kind of see some differentiation, that we then started preparing for. And then we presented, the first set in October and the second set now. I think it's very interesting that on the battery report, there are also the 4 companies, not just in silicon, but in materials, that have gotten the most investment to date. Mm-hmm. So I think that's just kind of an interesting thing to look at. And so, the investors who do a lot more diligence than we do all thought they were worth investing in.
Yep. And then if you go to the next one, I think, Aubert, this is our updated aggregate score, everybody, for all the silicon companies. So that we have covered so far, and our goal is to always update this, and we provided the information, but you can kind of see here Amprius and Scylla going blow for blow. In
the previous one, Amprius was a 3.3 total aggregate, and I think they went up from both Do We Like Them, the section up, and then a little bit also in Engineering Into the Box and Pain Point. So that's where they went from a 3.3 to a 3.8. It's kind of funny that they, even though the scores are pretty different in the different categories, they ended up identical in the average.
I viewed them trading blow for blows. Enovix is slightly behind. We can get like one of them Rock'em Sock'em robots thing going there. And then, Enovix, of course, behind slightly only. And then Enevate is, just like Aubert said, it's hard. I thought like some of the other companies have been hard to do research on, but Enevate was a royal one of just scouring LinkedIn, seeing if they did anything for the government, scouring.
I spent probably 2 hours through a lot of sort of back channel stuff trying to find anything that they'd ever done for like any type of grant proposal, registration, white papers, and they just they don't. If it's not patents, they don't tell you anything.
Yeah, they're very notoriously closed vests. Part of my job is to understand our competitive nature as well, and they are very, very, very hard to kind of put your finger on, which makes, from your perspective, correct, right? If you're that, closed book, it doesn't breed trust, right?
Yeah. And that's basically the Do We Like Them is we gave them, it seemed like they were overhyping for what we could find, and therefore we don't like it, right? I mean, that's really where the grading came from at the very end, and the fact that we just couldn't find enough information to justify liking.
Awesome. So at this point, right, I think it's good we come to the part where we just open up the floor. Type it in chat. I'll try to keep up with it. Ask it vocally. We'll try to answer it. Your comments, your questions, your thoughts. We're here to let's start the brunch org section, as Linda said.
We have an Enevate employee.
Oh yes.
You know what, Jill? I think Erica from Redivius actually mentioned you, that you were a buddy of hers that had worked there and had patents there. If you're still in the chat, I would love to hear a couple minutes from you about Enevate or anyone else from Enevate.
Oh no, you're putting me on the spot.
Yes. Let me just say, from how close were we? If you could quantify that, how do you feel? Were we way off mark, or were we closer to the right?
I think it's true that there's not a lot of public information, and most of the information that we do share out of the company is with, I used to work there. I just want to clarify that. And it's been about 6 months now. But anyway, now I work with Luke, who you saw in the driving in the Tesla.
Yeah.
On autopilot.
So let's see. So you guys, the data available on the internet about Enevate, there's not much. We do share more. They share more with people they work with. And one thing that I really respected about the company is when they were sharing that information with outside people, they were being real with the information. They weren't trying to make it like outside of what they can do. And I appreciated their honesty in the industry. So even though it's not public to everyone, I will say that they're honest to the people that they work with.
That's awesome. So. But were we close on the business structure?
Yeah, I think some of the information they have, like the images that you showed, are pretty old. Like those have been around since the beginning of the company, and there's definitely a lot of improvements in the technology since then. And some of the concerns that were brought up, I think, have been solved. But I don't want to share too much.
Oh no, of course, yeah,
of course, yeah, we understand.
And I guess Jeff and I both we try to navigate because especially me, I've worked with four people for most of the companies we talk about, and so I have to be really careful not to say things I know from confidential sources versus public. So absolutely understand. Thanks for talking. Really appreciate it.
Yeah, thanks for the presentation. It was great to hear.
Yeah. So now that we've picked on her, anyone else? I don't know, thoughts, questions, things you'd like to go over more? I know we started going really quick about halfway through because we were running out of time.
Can I ask a couple of questions?
Sure.
Please.
Yeah, great presentation, guys. So I was quite curious about the cost and the lifetime of the silicon batteries in general. So like, how do we compare to say $1 per kilowatt hour? I understand it will probably be higher because it's like a new tech, but also lifetime wise, how do they do now compared to say graphite based batteries?
There's been a lot of improvements.
Why don't you tackle lifetime and I'll tackle cost?
Okay, so as far as lifetime goes, there's been a lot of improvements. The real reason being is when silicon first came out, there wasn't a lot understood about, one, what is the correct electrolyte system for it, and two, what is the correct binder/electrode architecture for it. So if you look at silicon 10 years ago or 5 years ago, right, you're looking at probably 100 to 200 cycles with a pretty steep fall off depending on who you talk to. But nowadays, depending on, one, what type of silicon are they using, whether that's a silicon monoxide or a full-blown silicon nanoparticle, you can see anything from 300 to 500 in terms of a silicon battery's life. And that's really a combination of multiple components improving. So like FEC I brought up earlier was the big revolutionary one for silicon when it first came out inside of the electrolyte additives. But even nowadays, they've changed over to multi-package additive systems on top of doing actually completely different base solvent systems. So you get that's helping a lot with the passivation of the anode. And then on top of that, a lot of the companies have recognized that making a homogeneous slurry, reducing and changing and have a stratified particle gradient or size gradient are really helpful towards expanding the lifetime of those batteries. Because what you're doing now, or what you're seeing a lot of people do, is not try to go for the ultra high energy density in terms of the cell unless the application calls for it. And they're focusing more on getting, a large chunk of the silicon utilization, but not enough to where they're starting to break their electrode structures down. And then we got one here.
500 cycles was like, what C rate or like what calendar life would that be?
My guess is that's probably something on the lower side. That would probably be about C over 5. C over 5 to C over 10, somewhere in there.
Well, one thing to just mention, there's also a very wide range of silicon materials. I mean, everything from people are using bulk silicon, treated silicon, silicon oxide, treated silicon oxide, nano treated silicon oxide wire. I mean, nano wires. So there's a very wide variety, and so the answers change for all of those. From a cost perspective, you can get silicon oxide in graphite at moderate percentages, 15 to 40%, some places, and that's with the graphite ends up being pretty reasonable. It's like $30 to $50 per kg in smaller quantities, like not non-commercial quantities. I'm talking like 10, 25, 50 kgs. If you buy at that point, you can get those pricing. Pure silicon that's somewhat untreated tends to be $50 to $100 a kg in the same quantities. Treated silicon ends up being 100 plus. Silicon oxide, especially the good ones like Shinetsu in smaller quantities, are hundreds per kg, but they also work really, really, really well. And when you go to nanowires, I mean, those could be thousands of dollars per kg, but again, they work really, 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 really well. The other sort of additional costs with silicon tend to be things like you need special additives in the electrolytes. You know, lots of FEC is a great example. Other things like that can make other pieces of the cell cost more. And typically, you also have additional cost on the cell structural, processing of electrode pieces of it as well. So in general, it's plus cost plus performance, right? And that's what allows these to be plus performance enabling technologies. Yes, they cost more, but hopefully you can sell them at a pretty high premium to compensate.
Yeah. And then we got another chat in here, guys. This one's a big thing. We talk a lot about graphene lately, and like the question was pretty broad. It's what's graphene's role in batteries? I do a lot of carbon work. I can tell you right now, graphene is going to have a very either dominant role or very niche role dependent on the chemistry by which you are trying to apply it to, right? So right now, graphene, I think Panasonic actually, or is it LG? One of the two use a very high surface area, high aspect ratio graphene instead of going with pure, like Tim calls C65. The reason being is that high aspect ratio reduces the amount of junction points you have in the electrode, right? So resistance doubles for every particle junction point, right? So you want to increase the contact point to help reduce the total electrical conductivity resistance, but you also want to have a high aspect ratio, so you're not going from particle A to particle E. You have the opportunity of sending electrons from particle A directly in junction with particle C into the same vein. So for a lot of the more traditional chemistries, so lithium ion, high voltage, graphite, silicon, even in some of your solid state materials, because those are going to be looking for higher conductivity too, you'll see graphene seen as primarily as an additive or a protective layer on the primary material itself, but you will not see you won't see it as like a primary battery material. You'll see it as a supporting material primarily in batteries, right? Lithium air, it will probably be the conductive scaffold by which you decorate with catalysts for the lithium air battery to work. Lithium sulfur, same thing. It's going to be a support material for the active component in the cathode. I know there's a bunch of research out there about using carbon scaffold for lithium metal anodes. Even in that application, it would still be a support structure, although there's a lot of rabbit holes and problems associated with that kind of structure, but it's going to be a support material. And then another one we got Aubert is silicon volume constrained cycle life. You want to go on that one?
Oh, sure. So again, it depends on what you're using. And there's a big difference between a bulk silicon that has no room to expand, that, as Jeff said, grinds itself to death, versus the patterned or porous or structured electrodes or things like that do a lot better. I guess just offhand, I can say that I have seen in R&D, I've seen 800 cycles on majority silicon cells that work pretty well at decency rates. I've also seen much higher performance for rates and or energy density that fall apart before 100. So it just really depends on what you're trying to do and what you're building.
All right.
Hey, quick question. I just wanted to bring up a comment on Enovix. I think this might be a result of them having to go public and be fully disclose their data now, but they just made a presentation at AABC in California, and they had to come clean with, I think, an important issue that has to do with not just silicon, but solid state in general. There's a slide in their presentation saying that their core energy is 900 watt hours per liter, but when you put the stainless steel pack and the 3D structure, it drops all the way down to 550 watt hours per liter. And I think that's a key thing no one's talking about. Like QuantumScape doesn't talk about the fact that, yeah, they have great energy, but they need compression to keep. I see JR agrees with me. Yeah, her and I think have a similar feeling on all this. It's ridiculous, like the amount of hype there is in terms of they're making materials work by putting massive compression, and that is meaningless because the minute you have to include compression, your energy densities are lower. So what was really intriguing to me was Enovix did announce they're going to go after EVs, but then this blew my mind. They said our 55 amp hour targeted energy density is 690 watt hours per liter. And I know there's some people from Tesla on the call, but I'm like, but that's not even competitive with Tesla's new cells. So why are you paying all this extra money for silicon if you're not even going to get the volumetric energy that Tesla's manufacturing at scale today? And I think that's a big issue that the markets have to overcome.
Yeah, it is.
You got to make your silicon or your solid state or your lithium metal work without compression, or your energy densities cannot rival the current state-of-the-art automotive cells. And no one talks about it. Everyone puts in the footnotes or puts in asterisks, but the truth is, according to Enovix's own slide, their current cell format only delivers 550 watt-hours per liter.
Yeah,
because of that stainless steel compression.
I'll give everybody here a token piece of advice. Grab the two best things to determine energy density of your cell are going to be a scale and calipers. And you're going to take your cell, drop it on the scale, take that number, whatever it is, write it down, take your calipers, grab everything, write it down, take the energy off if you're an Arbin, a Biologic, a Macor, a Digitron, or whatever have you, and divide into the correct units.
But include the compression, Jeff. You got to include the stainless steel. So you're going to need Archimedes method, dude. Caliper is not going to work. You're going to have to take the whole compression thing, dunk it in a giant jug of water, and see how much water it displaces, because you got the nuts and the bolts, and you got these springs, right? That's why compression's crazy, right?
Yeah. So the thing about compression, guys, I'll give you an example. Automotive compression maxes at 1 ATM. That is the standard by which everybody uses. So if you are at, for example, if you are at 3 ATM, which names will not be named, you are very much exceeding the tolerances of the module that would fit into that application, right? Like we said before, and I've said before a few times, you can't think about this on a pure cell level. You have to think about it on a cell to module to everything level, right? If you have to build in hard metal fixturings in order to support the strength needed to get 3 ATM of pressure, that is more weight. More weight drops your module level energy density down, right? Conversely, if your thing is ultra safe, you can get rid of some of the safety issues, and that increases your module level energy density. So there's a bunch of trade-offs here that need to be taken into perspective. And when we talk about new chemistries, guys, you're going to see a lot of tricks, and I'll quickly run through them. One, people are going to quote 4 different kinds of energy density. They're going to just quote the materials itself, and that is the number you will see. They will quote a model based off a single layer or 3-layer pouch, where they said if everything is perfect and I buy everything that is amazing and top state-of-the-art from 10 micron aluminum to, ultra thin copper, this is what my energy density would be. They are going to quote a core energy density, which, Robert brought up, which is basically they ignore the packaging to give everybody a kind of frame of reference. Your average pouch cell Mylar packaging, the thinnest available is going to put you back about 3 grams in weight, or 2 to 3 grams in weight, depending on how your design and everything else. A 18650 will put you back 9.5 grams in weight, just based on the case of the housing. So people will quote core. And then the final one is you're going to see people who quote the total battery. And those are the ones where you're going to see numbers that are more or less in alignment. And I think Aubert here has been flashing this slide pretty vigorously.
I shared the previous version. So this is the full version that Jeff and I are still working on. Those of you that have been to previous talks, we've shown versions of this before. Basically, it's the manufacturing processes that you go through to make a battery, the different chemistries that currently exist for that, price points for a lot of the steps that we were able to find publicly. And then it's sort of performance metrics, and these are very loose, right? Some of these vary very wildly between different subsets of the technologies. Some of them are pretty clear, like lithium metal or basic lithium ion NMC. But then the performance metrics, and then sort of by application, what those match into based on the performance metrics. And the last thing we're actually going to add to this when we have time eventually is down here, we're going to slot in all the companies. So it'll have all the companies ping to kind of what their performances, cell technology, manufacturing process, and the whole kit and caboodle. So I just shared a public version of this that we think is sort of done. It doesn't quite have all of these technology points. Let me just pull that one up real quick. So the one I shared is this one, which is the one I was flashing earlier. So this one's done and available, and it's got some other process flow control, battery resource lists, and stuff like that we've tried to make public. All right, you can keep talking now, Jeff.
Another thing you guys got to watch out for with like just standard battery startups and stuff is really deviation. I call it the champion cell fallacy or something like that, where you basically you get shown a graph and you don't know how many cells went into that graph. You don't know if that was a power and energy cell. You don't know if what the failure rate is, right? Like those are the things you got to avoid, and it's something every battery startup is going to struggle with, right? You're going to have these people creating new materials. They made really cool materials at Aubert, you wanna stop the share?
Yeah. Oh, sorry. So this was the presentation, right? So I was just grabbing the share. You're right. I should stop sharing, but.
So the back to the train of thought, they're going to have this great material on a nanoscale level, right? Scylla is an example of this. Solid Power to an example, Extend is an example of this, and they're going to have to figure out how to create metric tons. I want you guys to think of what a metric ton looks like. Does anybody have a good idea in their head the size of a metric ton of material? Anyone?
Jeff, you got to talk about density. How light is Scylla's light powder? Come on.
No. We'll get to volume at another day. We just got to get to metric tons, right?
Well,
you guys,
if
the
you're
meter
looking
cubed of water.
Yeah, I mean, think of a train car. You have to produce enough of the same material to fill 8 train cars. Just think about that for a second. You talk to a lot of these companies, and they will produce stuff on maybe a kilo basis, right? But even scaling from making a kilo of really good homogeneous material to taking that 100 liter or 10 liter or 20 liter reactor and then pushing it to like a 1,000 liter reactor, suddenly your flow dynamics have changed. Suddenly your reaction rates have changed throughout the liter rate, right? Like there's a ton of these pain points along the process. So these are the things you kind of got to watch out for. And to Robert's point, right, like Scylla is a very low volume electrode. It's this super fluffy, super carbon scaffolded silicon electrode. They went with wearables, which I am fully for. They're announcing a wearable in the watch. I think that is a fantastic, the fact that Scylla was like, we're talking to GM, here's our car battery. Like, I am very happy they were like, we're going to put it in this wearable. It's going to be low volume. That's great because no battery startup, even people like Enovix or Scylla who have multiple pilot lines or anything, the volume is going to kill them that they would have to supply for certain applications. So it's going to be low volume. It's going to be low power, which means expansion is not going to be fast. You're going to get a relatively high silicon utilization rate. You're going to get relatively easy stresses on your binder system. They're probably using some elastomer to help contain and deal with some of the expansion. It is a fantastic road forward. But Scylla, they put it in this carbon structure. Carbon has a density of 1.5 thereabouts, and silicon's a bit higher, and you're going to have to take an average of that based on the content of each component, and then you're going to have to figure out how does that work volumetrically, and that's going to eat into everything, right? Not all materials, sometimes these super complex solutions come with a lot of downsides that aren't intrinsic, because all we do is we look at the energy. And the reality is you got to look at, if you're making a 200 micron thick electrode, you kind of got to factor that into your end result, right? So that's kind of my spiel on that, but I mean, we're still open to questions here. Anyone else?
And Jeff, just to comment, one of your topics earlier about safety, you guys have probably seen in your own testing, there's a heck of a difference between a nano-structured silicon with incredibly high surface area versus a low surface area silicon. It's all just electrochemical dynamic, right? Surface area and safety are an inverse relationship, and I think that's what Gio was trying to say at Enevate without giving too much away. I do have to give Enevate props because they did form an anode through the pyrolyzation to take away a lot of that silicon surface area to make it intrinsically more safe than a nanowire or nanoparticle thing. So I don't know if you wanted to comment on that. I know some of the work
I think, go ahead. Yeah. So I'll comment on safety. I'm going to approach it from more macro level, and Aubert and I were talking about this the other day. Everyone here agrees we're all moving towards LFP, right? For the current gen batteries. I don't think anyone here would disagree with that because LFP is more safe is what it is heralded, guys. We're going to just time out. 100 kilowatt battery pack versus a 65 kilowatt battery pack. it still goes boom real well. I'm going to just time out right there. Let's be real. If you have a lot of energy in a very constrained place, you are going to have a very excitable event, right? So just because your Tesla went from 100 kilowatts to 75 or 65, if it goes while you're in it, that's a lot of fire. So when we talk safety, everybody, we need to talk about relative safety, right? Safety.
And there's lots of other aspects, right? So there's less of a chance of different types of failure events, right? You can make it less likely of a nail pen causing a fire, less likely of a crash, less likely of another defect. You can make it so that it takes a longer time frame for a thermal event. You can make it take a higher thermal threshold for a thermal event. You can lower the impact of the thermal event. Fundamentally, with liquid electrolyte, you're going to have a thermal event. There's no way to get rid of that, right? So everything else is about the cost and the other performance metrics trade-offs for that relative safety change.
I think Luke has something to share.
Yeah, if I could comment for a minute. Let's say that you have no electrolyte in the cell. If you have just clean, washed, coated aluminum foil with nickel, particularly high nickel content coatings on it, you can actually grind this and burn it, and it supports a metal replacement thermite reaction. With no electrolyte, no lithium, it burns, and it actually burns over 1600 Celsius because it leaves behind molten nickel formations.
Mm-hmm.
And that's unrelated to being a lithium battery. That's just the thermite reaction. What I wanted to say though was we actually do stop. It was mentioned the Tesla pack, and if you induce thermal runaway, we actually do hard stop PPR tests for clients, and that's one of the main things our business does. And we use the calorimeter for quantifying the energy differences. But we use endothermic fillers in our potting. They're over 50% endothermic filler by mass actually, and it has a one-time bond cracking. It's a triple bond in off gases. So it's not a phase change that resets, but it's over 100 times more energy that it absorbs than phase changes that are resettable. And using this process, we hard stop propagation, including things like 5 separate 3-inch nail pens going into multiple cells in the pack. We do overcharge group sets to overcharge into runaway and pass PPR, and have great success for multiple aircraft clients and ground vehicle clients at hard stopping PPR, even in multiple initiations, even in, and of course we're testing at 100% SOC. Of course, they're cheater PPR tests when you do it less than 100%. Anyways, that's all I'll say about that. But we achieve it for all of our clients, or they don't go to production. They have hard passing PPR test requirements, or we don't roll forward with production.
Yeah.
Thank you, Luke.
Another thing that isn't really talked about, guys, with nanomaterials, is everyone here familiar with like dust fires or grain fires for silos?
I was just gonna say, yeah, there's definitely a surface area relationship here.
Yeah. So if you have a very high thermal burning material and you have it on a very small scale in an area, you get a lot of friction in a dry room, where the friction is going to be even higher because you don't have a lot of lubricant in the atmosphere around the materials. You will get grain dust kind of fire events. And to Luke's point, something burns at 2000 C and you get a lot of it. You're putting holes through things. Your containment is going to be expensive. Safety of the room is going to be really hard. Disposal is going to be really expensive, right?
So can I chip in?
Sure.
I do a lot of. I come from UL Underwriter Laboratories. I do a lot of battery testing. So what you exactly mentioning? These all parameters we encounter a day to day. So that's the reason our UL 9540A, the test standard, the cell level, we concentrate more on the deflagration hazard of the batteries, mostly. So that's like LFL, Pmax, lower flammability limit, Pmax, and also mostly burning velocity. These are the factors we concentrate more on, which are mostly related to dust and like the grain and dust industry. And also most of the sensors we use or analyzers we use mostly cater for those industries only. There is no specific things for this particular industry where we use for lithium-ion batteries. So that's one more thing. And also the major problem we have is disposing the burned batteries too. none of the dump yards don't want to take these things. There are so many issues there too.
Yeah, no, I mean, safety is extremely big. Even from a lithium metal perspective, guys, remember, lithium metal catches fire way better with water than it does with actual fire. Just to put things in perspective, right? Safety is going to play a big role. We all just went through an event where a bunch of Chevy Bolts and GM was hit with a huge recall, right, in the tune of billions of dollars. And that's why you're seeing even harder push to LFP, right? If you are a battery manufacturer and your margin is roughly 10%, right, the idea of having to replace that many batteries, that's several years worth of revenue that you will have to compensate. So the idea of going to a safer system is even more present or more present in everyone's minds, right? There is a lot on the safety side that just isn't A, talked about, and B, isn't really well explored, right? It's just being pushed. Aubert can tell you a lot of the time as they do safety stuff that energetic things are really, really unsafe.
On that topic of something not often talked about, it was mentioned a few times, combustion temperatures. But in this situation, we actually have electrically driven plasma because, for example, if we have a 10 kilowatt plasma cutter, we can cut through aluminum and stainless, really quickly, right? If any of you are metal workers. But this is because the temperatures are tens of thousands of degrees, not merely, say, like acetylene torch temperature, something like 2800 C. But we actually achieve tens of thousands of degrees because when you electrically pump conductive plasma, the moment an arc strikes or the moment there's flame, this is conductive now. And as you dump more electricity into it, it conducts better. So it's a positive feedback loop. It's why arc flash circuits tend to track maximum power, because of this feedback loop. They pull the pack to half voltage, true max power out. This allows you not to be limited by combustion temperatures, and it also affects LFP the same. Whether you're LFP generating the current or whether you're high nickel or any other cathode or anode, the electrical hazard and the plasma cutting effects are identical.
And the thing what I observed during our testing, also most of the thing which we don't discuss much even in these in forums is the gases coming out of these batteries. That's a major thing no one discusses. And if you see some of the chemistries do release hydrogen fluoride, which is a very dangerous gas, which no one talks about. The good thing about hydrogen fluoride is it reacts with the environment faster and it dissolves, but we still don't know. It's in a really a gray zone how it is dissolving or how much the hydrogen fluoride is coming out, how fast it is reacting with the environment, or like how far it can reach. These are the factors still running around the batteries, because we did some testing using HF sensors. We did identify some batteries have some chemistries release hydrogen fluoride.
So I can tag in here, guys. A lot of when we talk about specific safety events or gas generation or leakage or green or environment, really what we're looking at is basically a carbon calculation, right? None of us here are going to say that if we buy an electric vehicle, we are green. We still got to get energy to charge that electric vehicle from somewhere, and depending on where you live, the energy that we'll be providing for your electric vehicle is going to be dictated by wherever you're getting your energy, right? If you don't live near a nuclear power plant and you live near nothing but coal plants, 90% of the time you're charging your Tesla with coal energy, right? Which has its own carbon emissions, right? Batteries are just a store of technology, right? If it is storing, a store of energy, and if it is storing energy from heavily carbon producing power sources, then it has a carbon footprint attached to it, right? If it's from nuclear, it has an associated. If it's from solar, wind, etc., it has a different associated carbon footprint, right? So when you do these calculations, it's not just, what does the thing produce as it is a failure and going towards recycling. It is, where did the energy come from? Where did the materials come from? How were those materials produced? How was the battery produced? What went into producing that battery? What was the recycling like? What is the battery's use case? Is it active versus passive? How is it recycled? What does it do at the end of the day, right? So all of these factors actually have to come into play, right? It's just a store of energy. That's all it is. And it might take NMP, which is not great, to coat your electrodes. But it's all relative, right? Similar to the safety thing, when we energetic or exothermic events are exothermic regardless if it's LFP, NMC, silicon, nickel, they're usually bad. As long as there's enough energy, that event is very bad, right? A kilo of lithium is a lot worse of an event than a milligram of lithium, right? So it's all about the relative nature of it. So when you think about green technologies, I'd really say people need to avoid from saying something is super green until they actually understand the whole carbon life cycle analysis of it, right? Because your carbon life cycle analysis is going to have to take into variables like where did you put your factory? What did you do to the land that your factory took up? How far do you have to ship materials to that factory? And then where is your factory getting power? So like it's a very complex subject that actually goes pretty unrelatively noticed, and safety is an aspect in that, right? Because the safer the battery is, the less likely there is to be an active polluting event associated with it, right? If for example, a Rimac catches fire, that gets factored into the calculation, right? What are the odds of that pack going?
Iron phosphate car too, just as an example.
Yep, all of it, right? It's all the same regardless of the technology in terms of.
So Jeff, I have a question for you on your opinion. This is the huge battle between those who believe, like Tesla does, that you should have smaller cylindrical cells with their own fuse, where when each of those pops, it's a much less explosive reaction and you have cell-to-cell propagation, so you'll lose some cells but not the vehicle, versus this obsession with going to 80 amp hour cells, where if that thing goes, don't tell me you can prevent cell propagation. That's the dumbest thing I've ever heard.
150 amp hour high nickel content NMC prismatics that we're actively working on PPR prevention right now.
Really? How is that going? Just out of curiosity. That seems to me like a crazy problem.
It's going very difficult, but we're making headway.
Yeah, so where there is a will, there is a way. Is everybody here familiar with fire ratings for walls?
Yes.
Yeah. Okay. So my guess is the prevention tactics, to your point, aren't to save the rest of the batteries. The prevention tactics are to give enough time for a person or a living thing to leave the vehicle in a safe time. And I think
that's how a lot of OEMs define passing PPR as you had 60 seconds or 90 seconds. I think the German government rules 90 seconds. Wow. But many companies call this a past test. I call a past test, it gets no intervention and it stops propagating.
So
depending on the test, we'll have a plus variant so that you can have some additional cells that were initiated. Sometimes with 2170s, I'll do a +6 as also a pass, but that means no more than 6 cells went at any amount of time, given no additional efforts, to prevent the event.
Yeah, so like a good example of this is Solteria is a great example of a company that's taking a really novel approach to this. Basically, they're the company. You guys are all familiar with Lay's potato chip bags, I hope. Essentially, a small amount of aluminum or metal coated on top of a plastic substrate. They're trying to use that for electrode current collectors. And the main reason is when you get these really high exothermic events, the plastic shrinks and it pulls away from whatever was damaging the cell. So it's kind of tries to self-contain. Now, it has its own issues, and I'm not here to say they are the answer going forward. What I'm here to propose is that there is actually people coming up with a lot of novel ways, towards Luke's point, where it self-regulates to a certain extent, right? And the issue you have here is it is a hard problem, right? When you get something energetically going, it is very difficult to have it self-contain. That is just, unless you have, that's why you see a lot of these isolations in these pack designs are usually external methods to contain rather than the cell having a built-in way to contain.
So Jeff, I have a question. We got to visualize a world in where every vehicle is an EV, right? Mm-hmm. So this whole safety standard now that you have 90 seconds to get away from your car is interesting. But I don't see that playing well in a world where it's 100% EV. So I'll give you an example. I'm driving through a tunnel. There's a backup. There's a car crash. One car goes up. You're in a tunnel. And now every car is an electric car. Mm-hmm. So 90 seconds to get away from the first car that blows up the second, that blows up the next 10. I don't see that playing well. So I wonder whether people are going to have to rethink minimum safety requirements when it's not every 1% of vehicles on the road are electric, but every single car on the road is electric.
Jeff, I can answer this one because I have a fire protection engineering background, because mostly tunnel safety has separate safety standards. So any tunnel being built has to go through multiple wettings, like